Imagine for a moment that you are standing in a nondescript industrial park in Veldhoven, a town in the southern Netherlands that most people could not locate on a map if their lives depended on it. It is a place of flat farmland, bicycle paths, and gray skies that look as though they have been permanently installed by a melancholic set designer. But inside one particular building on this particular street, there is a machine so complex, so utterly singular in its function, that if someone were to walk inside and simply flip the wrong switch, the global economy would not stutter or hiccup, it would seize. Not metaphorically, not eventually, immediately. Within hours, the stock prices of Nvidia, Apple, Microsoft, Amazon, and every other technology company you have ever heard of would begin a downward spiral that would make the 2008 financial crisis look like a minor accounting error. Within days, the factories in Taiwan, South Korea, and the United States that produce the chips powering your phone, your car, your hospital's ventilators, and the data centers training the artificial intelligence models that are supposed to define the next century of human civilization would grind to a halt. Within weeks, the supply chains for everything from electric vehicles to fighter jets would begin to collapse. And all of this would happen because of a single company, in a single building, in a single Dutch town that has achieved something no corporation in modern history has ever accomplished. A total, absolute 100% monopoly on the most important manufacturing process on Earth. That company is ASML, and the machine is the Extreme Ultraviolet Lithography System. And the story of how we got here is so absurd, so terrifying, and so darkly comedic in its implications for the future of our species that it deserves to be told in full. To understand why this matters, you first need to understand what this machine actually does. And to do that, you need to understand the problem it was built to solve, which is, quite literally, a problem of physics so difficult that for decades, the smartest engineers in the world insisted it could not be solved at all. We are talking about printing circuits. That is what lithography is at its core. You take a silicon wafer, you coat it with a light-sensitive material called photoresist, and then you shine light through a mask that contains the blueprint of a microchip, and the light etches that pattern onto the wafer. It is, conceptually, not unlike using a stencil and a spray can to paint a design on a wall. The problem is that the design we are trying to paint is now so small that it defies comprehension. We are not talking about tiny. We are talking about transistors measured in single-digit nanometers. A nanometer is 1/1000th of a meter. To put this in perspective, if you took a single human hair and sliced it lengthwise into 100,000 pieces, each piece would be roughly 1 nanometer wide. The transistors on the most advanced chips being produced today are 3 nanometers across. In a few years, they will be 2 nanometers. And soon, they will approach 1 nanometer, at which point we are literally engineering structures that are only a few dozen atoms wide. This is the scale at which quantum mechanics begins to laugh at your classical understanding of how the universe works. Electrons stop behaving like predictable little billiard balls and start behaving like probabilistic ghosts that tunnel through barriers they should not be able to pass. At this scale, the very concept of a wire or a switch starts to dissolve into the fuzzy, probabilistic foam of the subatomic world. So how do you draw a pattern that small? You cannot use normal light. You cannot even use the ultraviolet light that older lithography machines employed. The wavelength of that light is simply too large. It would be like trying to paint the Mona Lisa with a house painting roller. You need light with a wavelength so short that it barely qualifies as light at all. You need extreme ultraviolet light, which has a wavelength of 13.5 nanometers. This is not the kind of light you can generate with a bulb. This is not the kind of light that exists naturally on Earth in any meaningful quantity. To generate this light, ASML's engineers had to devise a process so insane, so fundamentally violent, that it sounds like the plot of a science fiction novel written by someone who was angry at physics. Here is how it works. Inside the machine, there is a droplet generator that shoots tiny droplets of molten tin at a speed of roughly 250 feet per second. These droplets are about 25 microns in diameter, which is about half the width of a human hair. As these droplets fly through a vacuum chamber, they are hit by a high-powered carbon dioxide laser. But they are not hit once. They are hit twice. The first pulse hits the droplet and flattens it into a pancake-shaped disc. Then, a few nanoseconds later, a second, far more powerful pulse hits that flattened disc and vaporizes it instantly, turning it into a plasma that burns at a temperature of around 220,000 degrees Celsius. That is roughly 40 times hotter than the surface of the sun. In that instant of annihilation, the tin atoms are stripped of their electrons, and as those electrons recombine with the ionized nuclei, they emit a flash of extreme ultraviolet light. This flash lasts for a few billionths of a second, and that light, that precious, barely there light, is then collected by a series of mirrors, because lenses cannot be used at this wavelength. Lenses would simply absorb the EUV light, so you must use mirrors, and these are not ordinary mirrors. These are the most perfectly polished mirrors ever created by human hands, coated with dozens of alternating layers of molybdenum and silicon, each layer only a few nanometers thick, polished so flat that if you scaled one of these mirrors up to the size of Germany, the largest imperfection on its surface would be less than 1 millimeter high. The light bounces off these mirrors, passes through a mask that contains the chip design, and finally strikes the silicon wafer, which is mounted on a stage that moves with a precision measured in picometers, which are trillionths of a meter, a scale at which you are now contending with the thermal vibrations of individual atoms. And this entire process, this Rube Goldberg machine of cosmic violence and atomic precision, must be performed in a vacuum, because air molecules would absorb the EUV light before it could reach the wafer. It must be performed in a temperature-controlled environment so stable that a fluctuation of a few thousandths of a degree would ruin the alignment. It requires hundreds of thousands of components, miles of wiring, and a supply chain that spans the entire globe. From the German optics company Zeiss that produces those impossibly perfect mirrors, to the American company Cymer that provides the laser systems, to the Japanese and South Korean companies that produce the specialized sensors and materials. A single EUV machine costs over $350 million. It takes 2 years to build. It requires 4 jumbo jets to transport, and it is roughly the size of a double-decker bus. And there is only one company on Earth that can build it. That company is ASML, and they have a 100% monopoly on this technology, not 90%, not 99%, 100%. If you want to build a microchip using the most advanced process nodes, which is to say, if you want to build any microchip that powers anything that matters in the modern world, you have no choice. You must go to ASML. You must wait in line. You must pay whatever they ask. And you must hope that the geopolitical winds do not shift in a direction that prevents them from delivering your machine to you. How did we allow this to happen? How did the entire future of human technology become bottlenecked through a single corporation in a country more famous for tulips and windmills than for global technological hegemony? The answer is a combination of physics, economics, and a kind of corporate fatalism that is almost beautiful in its brutality. In the 1990s and early 2000s, when the semiconductor industry realized that traditional lithography was approaching its physical limits, several companies tried to solve the EUV problem. Intel poured billions of dollars into research. Nikon and Canon, the Japanese giants that dominated the older generations of lithography equipment, made attempts. But the physics were simply too punishing. The engineering challenges were so vast, so multidimensional, that one by one, the competitors dropped out. They concluded that the technology was not ready, that the cost was too high, that the risk was too great. ASML, which was at the time a relatively modest Dutch company, made a different bet. They decided that EUV was not just possible, but inevitable, and they committed everything to it. They formed a consortium with Intel, Samsung, and TSMC, pooling research resources and sharing the financial risk. They acquired Cymer, the American laser company, to secure the light source technology. They partnered with Zeiss, leveraging centuries of German optical expertise. And they spent over 2 decades and more than $10 billion solving problem after problem that experts had declared unsolvable. By the time the first commercial EUV machines were ready for delivery around 2017, the competition had effectively ceased to exist. Nikon and Canon still produce older generations of lithography equipment, but they never cracked the EUV code. They gave up. And in giving up, they ceded the most critical choke point in the global economy to a company that now has no rivals, no substitutes, and no checks on its power. This brings us to the Geopolitics, which is where this story transforms from a fascinating tale of engineering triumph into a nightmare of strategic vulnerability that should keep every policymaker in Washington, Beijing, Brussels, and Taipei awake at night. Because when one company controls 100% of a technology that 100% of advanced chip manufacturing depends upon, that company does not just have commercial power, it has geopolitical power. And the country where that company is headquartered does not just have a successful export, it has a weapon. The United States understood this long before most people did. Beginning in the Trump administration and accelerating under Biden, American officials began pressuring the Dutch government to restrict ASML from selling its most advanced EUV machines to China. The logic was straightforward and brutal. Advanced semiconductors are the foundation of modern military power. They go into hypersonic missiles, into artificial intelligence systems that can target enemy assets, into the supercomputers that simulate nuclear weapons. If China could simply buy ASML's EUV machines and start producing 3-nanometer chips at scale, the technological gap between the Chinese military and the American military would narrow in ways that Pentagon planners found unacceptable. So the United States leaned on the Netherlands. Hard. They used export control laws, diplomatic pressure, and the implicit threat of restricting American components that ASML needs for its machines. And the Dutch government, after much internal debate, capitulated. ASML was effectively barred from shipping EUV equipment to China. China, which has invested hundreds of billions of dollars in its domestic chip industry, which has made semiconductor independence a national strategic priority, cannot buy the one machine it needs to achieve that independence. Not from ASML, not from anyone, because no one else makes it. The irony is almost too perfect. China can build aircraft carriers. It can build space stations. It can build high-speed rail networks that put the rest of the world to shame. But it cannot build a 3-nanometer chip without a machine that only one company in the Netherlands can produce, and that company is not allowed to sell it to them. Meanwhile, in Taiwan, a different kind of geopolitical calculus is unfolding, one that is equally dependent on ASML's monopoly and equally precarious in its implications. Taiwan Semiconductor Manufacturing Company, or TSMC, is the most advanced chip manufacturer in the world. It produces roughly 90% of the world's most advanced processors. Apple chips, Nvidia chips, AMD chips, the processors in your iPhone, in your gaming console, in the servers running the large language models that everyone is now so obsessed with, they almost certainly came from a TSMC factory. And TSMC's ability to maintain that dominance is built on a foundation of ASML EUV machines. TSMC was one of ASML's earliest and most aggressive investors in EUV research. It has more EUV machines than any other company on Earth, and this has created what strategists have come to call the Silicon Shield. The theory goes like this. Because the world's most advanced chip production is concentrated in Taiwan, and because that production depends on ASML machines that cannot be easily replicated or relocated, the entire global economy has a vested interest in Taiwan's security. If China were to invade or blockade Taiwan, the disruption to TSMC's production would not just be an economic crisis, it would be an economic apocalypse. The United States, Europe, Japan, and every other major economy would be dragged into the conflict, not out of abstract commitment to Taiwanese democracy, but out of sheer economic self-preservation. Your iPhone would stop working. The cloud would stop computing. The military supply of advanced chips would dry up. The world would be forced to respond. In this sense, Taiwan's security is guaranteed not by its military, which is tiny compared to China's, but by the fact that it hosts the factories that ASML's machines make possible. It is a deterrent strategy based not on nuclear weapons, but on supply chain hostage taking. And it works because there is no alternative. There is no backup plan. There is no second source for 3 nanometer chips. There is only TSMC and there is only ASML, and the two are locked in a symbiotic embrace that holds the global economy in balance. But what if that balance is disturbed? What if it is not an invasion or a blockade, but something far more mundane? What if an earthquake hits Taiwan and damages TSMC's fabs? What if a fire breaks out at ASML's single factory in Veldhoven? What if a pandemic or a trade war or a shipping crisis disrupts the supply chain for just one of the hundreds of thousands of specialized components that go into an EUV machine? What if ASML's engineers, who are among the most specialized and irreplaceable workers on the planet, are unable to travel to install or maintain these machines for even a few weeks? The fragility of this system is almost impossible to overstate. We have concentrated the entire future of artificial intelligence, of cloud computing, of autonomous vehicles, of advanced weapon systems, of everything that defines modern technological civilization into a supply chain that has more single points of failure than a Soviet-era power grid. And the most critical of those single points is a company with $12 billion in annual revenue. To put that in perspective, that is less than 1/10 of Apple's quarterly profit. It is less than the market capitalization of a mid-tier American tech company that most people have never heard of. And yet this relatively small Dutch company holds the keys to the kingdom in a way that no oil company, no bank, no pharmaceutical giant, and no government has ever held before. If ASML stops, everything stops. Nvidia cannot design chips that no one can manufacture. Apple cannot sell phones that contain processors that do not exist. Microsoft cannot run data centers on hardware that cannot be produced. The entire edifice of modern technology, this towering cathedral of digital capitalism that we have spent 50 years constructing, rests on a foundation that is, in essence, a single building in the Netherlands. And here is where we arrive at the philosophical core of this story, the part that should make you feel something between awe and existential dread. We like to tell ourselves stories about technological progress as if it were a natural force like evolution or plate tectonics, something that happens inevitably and distributes its benefits broadly across humanity. We imagine a world of competition, of innovation, of many companies racing to build many solutions, with the best ideas winning out in a kind of Darwinian marketplace. But the reality of EUV lithography reveals a very different picture. It reveals a world in which progress has become so difficult, so expensive, and so dependent on esoteric expertise that it has consolidated into a single path, controlled by a single company, located in a single country. We did not arrive at a resilient, distributed system for producing the most important technology of our age. We arrived at a bottleneck, a stranglehold, a point of maximum vulnerability dressed up in the language of corporate success. ASML is not a villain in this story. They are brilliant engineers who solved a problem that everyone else gave up on. But the system that elevated them to this position, the system that allowed one company to become the sole gatekeeper of the entire semiconductor industry, is a system that should terrify anyone who thinks about the future. Because the future we are building, the future of artificial general intelligence, of quantum computing, of biodigital convergence, depends on our ability to keep making chips that are smaller, faster, and more efficient. And that ability for the foreseeable future depends on a machine that only one company can build, using components that only a handful of other companies can make, in a supply chain that spans the globe but terminates in a single factory floor in Veldhoven. We have, in other words, bet everything on a very small number of very complex things continuing to work perfectly forever. We have taken the vast, distributed, redundant systems that characterized earlier eras of industrial production and replaced them with a hyper-optimized, hyper-concentrated architecture of genius and fragility. We have created a world where the difference between a functioning global economy and a cascading technological collapse is the operational continuity of a machine that requires a plasma hotter than the sun to print patterns smaller than a virus on a wafer of silicon. And we have done this not because we planned it this way, but because the physics demanded it, because the economics rewarded it, and because no one stopped to ask whether concentrating this much power in this few hands was a good idea. It is not a good idea. It is a terrible idea. It is the kind of idea that future historians, if there are any, will look back on with the same bewildered horror with which we regard the architects of the pre-2008 financial system, who built a global economy on complex derivatives that almost no one understood, and that turned out to be catastrophically fragile. We are doing the same thing with chips. We are doing the same thing with AI. We are building systems of unimaginable complexity on foundations of unimaginable concentration, and we are telling ourselves that because the engineers are smart and the stock prices are high, everything will be fine. But everything is not fine. Everything is precarious. And the precariousness is not a bug. It is the feature of a system that is optimized for efficiency and speed at the complete expense of resilience and redundancy. ASML's monopoly is not just a business story. It is a parable about how we build the future. It is a warning that when progress becomes too hard for many to attempt, it becomes the province of the few. And when the few control the means of progress, they control the future itself. Right now, that future is being built in a quiet Dutch town by a company that most people have never heard of, using a machine that sounds like science fiction, but is in fact the single most important piece of capital equipment on Earth. And if you find that thought comforting, then you have not been paying attention, because comfort in the face of such concentration is not optimism, it is complacency. And complacency in a system this fragile is the most dangerous thing of all. The next time you look at your phone, or read about the latest AI breakthrough, or watch a stock ticker climb higher on the promise of technological revolution, remember the molten tin. Remember the plasma hotter than the sun. Remember the mirrors polished to atomic perfection. And remember that all of it, every bit of it, depends on a single building, in a single town, in a single country, where a handful of people are doing something that no one else on Earth knows how to do. That is not a revolution. That is a bottleneck. And bottlenecks, no matter how impressive the engineering that created them, have a way of breaking when you need them most.